Thank you. All right, thanks for the organizers. Allow me to give a second talk. And I very much appreciated the stay already here for several days in the past week, and hope that the rest of the week would be as much enjoyable or even more so. So what I'm going to talk about today is regarding this multi-messenger aspects of these R process sources. And Jim, in his talk following me, will give you a very detailed account of the historical development of the R process. I'm only going to mention some aspects of it. The details of the talk is again based on the two papers I wrote with two of my former students, Gang Guo and Menru Wu. Basically, one in Physical Review Letters last year, and the other one is earlier this year. We sort of already started the discussion about supernova last week, and everybody knows that a massive star at the end of its life undergoes gravitational collapse of its core, and at least initially would make a neutron star. And because you make such a compact object, a lot of gravitational binding energy will be released. And we also know that because the high temperature and density encountered during the collapse, the most efficient way to release this energy is through standard model, by emitting neutrino, antineutrinos of all 6 species, 3 flavors, neutrino and antineutrino. And this basic picture has been confirmed by the detection of neutrinos from supernova 1987A, which lasts about 10 seconds or so. You only detect the electron-antineutrinos, but you use the energetics, the number of events, you find out that the multiply by a factor of 6, you get back about this much energy, accounting for the gravitational binding energy. Now, that is obviously thinking about a single star, and just like human beings, stars have their own sociology. Quite a few of the massive stars, actually mostly half of the massive stars are actually formed in binaries. Now you imagine that the 2 massive stars in a binary, each of them undergo supernova explosion and produce a neutron star. And each of the explosions are pretty tame in the sense that they didn't disrupt the binary. So you ended up basically with a neutron star binary. And so this kind of neutron star binary, obviously, we're now going to be the remnants of these 2 original massive stars. They go around each other and they radiate gravitational waves. And the detection of the gravitational wave from a pulsar pair has been detected in the 80s and was verifying Einstein's prediction about the gravitational wave radiation in that way. And so obviously we know that the gravitational wave has also been directly detected by LIGO, et cetera, by these type of events. And so as the 2 neutron stars go around each other, eventually the orbital shrinks because of gravitational radiation. Eventually, the 2 stars will merge. And during the merging process, what you see is that quite a bit of the material from the original neutron star will be tidally disrupted by gravitational tides. And these tidal tails obviously contain very neutron-rich material. And also, the color coding is a little bit kind of counterintuitive. Actually, this bluish, purplish color means very hot. Okay, like at the end of the purplish end, you have tens of mega electrons, 10 MeV temperature, whereas the reddish thing is more like 100, more like a kilovolts, hundreds of kilovolts kind of temperature. But nevertheless, you see that this merged material during the tidal disruption of these 2 neutron stars, you have very hot material, and initially, obviously, density is also very high. And it also is very neutron-rich because it's essentially just neutrons. And these material will undergo basically rapid neutron capture process, which is called the R process. And eventually they can make very heavy elements. And also the other thing you recognize here is that because you initially have orbital motion, you have an orbital angular momentum. So that defines the plane, which is perpendicular to the original angular momentum axis. And the material disrupted during the merging process, quite a bit of it is just spread out in this plane. And that will eventually become an accretion disk, which will go on to whatever remains after the merging of the 2 neutron stars. But the other thing I want to recognize is that the time scale of all this process takes very quickly, of 4 to 10 milliseconds or so, okay, the last phase where the disruption is happening. Now, eventually the 2 neutron stars, because the combined mass typically supersedes the mass for a stable neutron star. So eventually the central object will become a black hole. As I said, that whatever the material disrupted during the merging will form some kind of accretion disk, basically it's rotating around a central axis. And the interesting thing is that this material in the accretion disk is undergoing lots of heating, be it by a viscous frictional thing or by neutrinos. And this heating will essentially evaporate this material. And again, this material is very hot and it's very dense initially. And as it puffs off the accretion disk, it undergoes nuclear synthesis as well. Same sort of kind of the rapid neutron capture kind. The other thing is that typically whenever you talk about neutron stars, you also talk about the magnetic fields. After all, most of the neutron stars are observed as pulsars. And the pulsars is essentially magnetized rotating neutron stars. And as the magnetic dipole rotates, you just see the pulses coming at you as radio waves. So you have magnetic fields for sure. And the accretion disk will be threaded by the magnetic field lines. And these magnetic fields tend to launch these so-called jets, basically in the direction of the rotational axis as well. And these jets are high energy phenomena. Basically, you can induce lots of shocks. And these shocks are places where you can accelerate charged particles. And these energetic particles, for example, for electrons, if it's accelerated to very high speed, it can upscale the photons by inverse competence scattering. And this is how you see gamma ray bursts come out of these kind of environments. Okay. And so this is really, as I said, a multi-messenger kind of a source for observations. And the kind of thing which people already figured out is gamma ray bursts associated with the jets and gravitational wave associated with the in spiral before the merging and right after the merging as well. But the part people didn't really pay much attention to until much recently is about the nuclear synthesis signature, which is the rapid neutron capture process. I'm just going to show a simple movie over here to show you that how does the R process really happens in a schematic way. So this is a chart of nuclei. The horizontal axis is the neutron number, and the vertical axis is the proton number. And so each nucleus is basically identified as one of the points on this chart. And these solid squares represent the stable nuclei you can have. Basically, it's about several hundred of them. Okay, you can count on them. These are the stable ones we have in nature. And the shaded region, essentially, by nuclear systematics, any kind of a bound form of neutrons and proton combination are basically sandwiched between these regions. Okay, and so as I say that the neutron star ejecta from this kind of merging process start out very hot. 10 gigakelvin essentially is about 1 mega electron volts. The density here is almost 10 to the 13 gram per cc. And under those conditions, the material, because it's extremely neutron rich and very high temperature and density means that all the electromagnetic and strong interactions are statistical equilibrium. You can just do statistical physics, nuclear statistical equilibrium. You see that the most of the nuclei beyond the neutrons are mostly in the form of mass number around 130 or so, peaks around there. Okay, and that is essentially distributed around this edge, the lower edge, the neutron-rich edge of the possible form of a nuclei. And so now the material expands away, the temperature drops, the density drops. You can see that this is essentially the evolution of the temperature. And you can also see the monitoring the temperature indicators on the top. And you can also see that how the nuclei distribution is going to shift as well. So initially it doesn't change very much, just local arrangements. Eventually just takes off, neutron capture just moves up, and beta decay also sets in. And eventually you capture all the neutrons, and these extremely neutron-rich stuff undergo fission and just go down there. And eventually you end up with a nuclear distribution like this. You have two characteristic peaks. And if you remember any of the nuclear structure you learned earlier, there are two magic neutron numbers. One is 82, the other one is 126. They're extremely stable. These two peaks around the mass number 130 and 195 also are due to the existence of these two magic neutron shells. Okay, so that is essentially how the R process will take place in this type of environment. Now, I'm going to bring you to high school chemistry. The interesting thing is that this periodic table, obviously, we now know essentially how each and every element can be made in nature. And this R process kind associated with neutron star merger. In particular, as I mentioned, mass number 130, there's a peak, and mass number 195, there's another peak. There are two special boxes on periodic table. The one is with atomic number, the proton number go from 57 to 71 and expanded over here, started with lanthanum, and it was lutetium. And the other one starts with atomic number or proton number 89, end up with 103, so this is actinium. One is called the lanthanides, the other one is actinides. And if you remember, these elements in atomic form, they have these electronic shells outside of them. These two series of elements are special because they are the only ones with F shell. Orbital angular momentum L equals 3 becomes available for electrons to occupy. And 2L plus 1 is 7. 2 multiplied 2L plus 1 is 14. So there are 14 different ways you can arrange these electrons when these elements are around to form atoms. And if you have so many electronic configurations, the photons, when they try to talk to these electrons, have so many ways of interacting. That means the cross-section for the photons to talk to these elements when they are in atomic form are extremely large. And in comparison, let's say that we typically think about the nickel, iron, those kind of elements, with mass number around 60 or so, made in supernova. Those kind of cross-section, or the astronomical parlance would call it opacity, is at least 1 order of magnitude lower compared with these guys. So they are extremely opaque. So now you imagine this material initially was made from very neutron-rich nuclei. And these neutron-rich nuclei obviously will decay back towards stability. And sometimes they decay to excited states and they emit a gamma ray, and these gamma rays cannot escape readily, so they thermalizes, so heats up the material. Actually, that's essentially how you see that this temperature is not monotonic. At this moment on, it actually gets elevated. That's because of the heating of this decay. And typically, when you beta decay, you obviously produce electrons. The electron does not obviously escape either. Its kinetic energy gets thermalized. So all that heating is essentially goes up into this bump over there. I mean, that heat cannot readily escape as photons, as I said, because this group of elements you made are so opaque. You have to wait until the material thin out to lower density, also accompanied by lower temperature. Eventually, you will let it go. That time scale for expansion takes on the order of days. So you expect somehow this material will become opaque to photons several days after the event of the merger. And this is essentially the entire multi-messenger picture. Actually, the paper was written actually before the first discovery of a neutron star merger event in all these glorious details. So first of all, as I said, that the two neutron star merge, emit gravitational waves, and then you form this kind of accretion disk around the black hole. The disk material gets ejected, or the tidal tail gets ejected. Those make our process nucleosynthesis. And as it expands and decays, you power this optical display, which is called a kilonova, because the energetics is some 1,000 times the nova brightness, also typical. And that is going to be days after. But concomitant with the gravitational wave signal, you already see the launching of the jet. As I said, that the jet accelerates very energetic electrons, and these things upscatter the photons in the environment, the gamma rays. You'll see gamma ray bursts. And back in August 17th, 2017, we see, first of all, the gravitational wave radiation from that binary neutron star system. And within a few seconds, we also see the gamma rays. And within a week, we also see the kilonova display from the radioactive nuclei made in the R process in the same event. Okay, so that's the great thing about this multi-messenger observation of these very exciting environment. Now, what I'm going to tell you about is an extension of the same kind of model. I mean, you can see that the general structure of all this is that you have an accretion disk surrounding a black hole, and you have jets coming out perpendicular to the disk and do wonderful things like gamma ray bursts. And the ejector from the disk, if it's very neutron rich, you ended up making these unprocessed nuclei. So that's how you can observe it in the case of the two neutron stars. There's nothing obscuring this thing because the two neutron stars have nothing surrounding them. But you can also see that the same type of engine can operate inside a massive star. We understand that it's a very tough problem to understand how these stars explode. And nowadays, the supernova modeling has progressed to such a degree of certainty that if your progenitor mass is 20 times less than the sun, 20 solar mass or less, we know pretty sure that the neutrino-driven explosion more or less can do it. But the thing is that if it's above 20 solar mass, then it becomes very uncertain. You can imagine that basically when the neutrinos are trying to heat the material above the neutron star and they try to push it away, the other material from the envelope is keep piling on to the central object. And eventually, if a star somehow is in such an unfortunate situation, the raining down of the material will overwhelm whatever the pressure can be supported by the neutrinos, that the star is not going to explode. Instead, the central object will collapse into a black hole. And we also know that the massive stars always just rotates. The sun rotates, okay? So all stars rotate. And during the collapse, rotates can only more or less gets faster if it doesn't stay the same. So they always have angular momentum. So material falling from the envelope going to the central object, they do not go on a radial trajectory. They always have to preserve angular momentum. So in the end, they end up in a disk. So this kind of disk situation is always going to happen in this kind of a model, so-called collapsar. So you collapse into a black hole rather than a neutron star. And the material surrounding in the stellar envelope surrounding the black hole is going to eventually fall into an accretion disk. And this thing is, again, going to be in the same kind of situation. The black hole accretion disk is going to be very hot, and it's going to evaporate material either by viscous heating or by neutrino emission, whatever the way it is, it will be pump out material like that. The only difference between neutron star merger and this kind of environment is that is the material neutron rich enough? Neutron star, is neutron rich enough because it's originally made of neutrons, right? So in this case, the neutron richness is guaranteed by the density of the disk. If you pour a lot of material onto the disk becomes very dense. And under those conditions, you can show by chemical equilibrium, electrons are extremely degenerate. When the electron degenerate and very energetic electron capture on the proton happens, and it just neutralizes the disk, okay? So eventually, what kind of material you're gonna make, whether you're able to do the same thing as in the neutron star merger case, making things like, mass number 130, 195 also, those two peaks, depends on how fast you are accreting the material. The larger the accretion rate, the denser the accretion disk, the more degenerate the electrons are, and the more neutron-rich material will be puffed out of the neutron star, puffed out of the accretion disk. Okay, so in this diagrammatic way, so this shows the mass accretion rate. And initially, if the rate is extremely high at this level, then you can see that the accretion disk is extremely degenerate in terms of electrons. Electron degeneracy, the redder or purplish means the more degenerate. And the electron fraction measures the neutron richness. The lower the electron fraction, the more neutron rich it is. Again, the purplish thing means it's extremely neutron rich. But later on, imagine that the envelope has mostly accreted onto the disk already. The accretion rate will drop, the density becomes less, and essentially you no longer become neutron rich enough. So you no longer make the rapid neutron capture heavy elements anymore. You basically stop more or less like a nickel and iron group. Okay, so that is essentially the picture. Now, in this kind of environment, you say, how can I see the signature of the R process? Because you see, unlike the neutron star merger, as I say, it's surrounded by nothing. The material containing the R process material can expand and shine in the light several days later or about a week later, in this kilonova thing, you can see it immediately. But this kind of collapsar is surrounded by tens of solars of material. You can't possibly see through it, right? Well, the interesting thing here now is that we have the neutrinos. Neutrinos can do the probe for us. So what's happening here is that the kind of wind puff off from the neutron black hole accretion disk, they will contain radioactive material. As I say, they initially made it very neutron rich. They will beta decay. Regular beta decay produce electron antineutrinos, okay? Low energy, typically like several MeV up to maybe like 8 MeV or so, okay? And then we say that the jet perpendicular to the disk is a great place for accelerating charged particles, like proton. If protons get accelerated to high speed, they collide with each other, they will make pions. When pions decay, they make muons and muon neutrinos, and muon decay makes electron neutrinos. This is how we make beams of neutrinos in accelerators, right? And now you think about it. If the electron antineutrino over here undergo flavor oscillation, it turns into muon antineutrinos. It'll seek an extremely energetic muon neutrino produced in the jet. They annihilate each other. And that will leave some kind of a signature, right? The signature will depend, obviously, on the angle at which these two neutrinos will meet and the energy of each other, etc. And eventually, you should be able to produce a signature for that. So let me just recapture. So the production mechanism for these high energy neutrinos are either proton-proton collision or proton-gamma collision. You produce pions. Pi plus gives you mu plus and the mu neutrino. Pi minus gives you mu minus and the mu antineutrino. And then you have the sequential decay of the mu plus and the mu minuses, give you further neutrinos of the electron kind and the muon kind. And typically, the neutrino energy able to be produced in this kind of a process is 5% of the rest frame proton energy. And then you have the boost factor because the jet is relativistic. You can easily get to maximum possible, at the PeV level for these neutrino energies. Now, the annihilation has a very interesting structure in terms of its interaction between the original high energy mu neutrino and the low energy mu antineutrino oscillated from the beta decay neutrinos from the unprocessed material, which is the Z resonance. Neutrino antineutrino can go through a Z resonance. The center of mass energy depends on each of the neutrino energy and the angle they intersect with each other, 1 minus cosine theta. You can see that because I explained the neutrino of the low energy kind come from beta decay. The beta decay has a maximum point, right? Those beta point decay energies at most 8 mega electron volts also for these typical nuclei we have. And the angle for intersection can only go by head-on collision. So there is a limit for cosine theta, 1 minus cosine theta. But from this calculation, you see that this process, which will go very efficiently if you go through this Z-naught resonance, the Z-naught resonance can only occur if your high energy neutrinos is more than 260 keV. Below that, you never excite this Z-naught resonance. You will not see as much on effect. So this is the spectral signature you're going to see. Okay. So this is essentially in somewhat the detail. Sure. Sure. So I'm going to explain now. So I'm talking about the muon neutrinos because muon neutrino is a dominant production mechanism in this particular model. And I'll explain now. All right. Okay. I'll talk about the other things later. All right. So you can see that why the muon neutrino, very good question. This essentially picks up on that. Why muon neutrino is mostly the dominant production? So first of all, the P gamma reactions has a lower threshold. It dominantly produces pi pluses. Pi pluses gives you the mu plus. Mu plus associated with mu neutrino. That's it. The other one is that what about the aftermath? When you have the mu plus, you can decay, right? But pion decay much faster. Muon decay a bit much later because the lifetime is different. And all these particles inside a strong magnetic field. And when charged particles go inside the magnetic field, the synchrotron radiation cools these particles. So during the time you wait for the muon to decay, the energy has been lowered. So this is why the suppression of the muon antineutrino comes about, because the pions initially produced is being suppressed. I mean, initially, the muons initially produced from the pion decay has been cooled. So this is essentially shown in here. So if you look at the comparison between the neutrino sector and the antineutrino sector, And let's focus on the without annihilation yet. Okay, so without annihilation, no annihilation, these dashed curves. The anti-neutrino sector is a red curve. The neutrino sector is the solid black curve. And the extra thing over here is because of the P gamma reactions. That's the only kind of a dominantly produce pi pluses. As I say that because you have these two reactions, this basically goes through delta resonance. Delta resonance decays by pi plus, right? And these ones, then you have threshold. Then you have to produce extra pions and all that. In that case, the pi plus pi minus modulus equalizes. But this one is only favors the pi plus, right? Okay. So the same reason favors the muon flavor compared with the electron flavor. You know, this red curve over here is the muon flavor, and the solid curve is the electron flavor, because electron production has to wait until the muons to decay, and the muon decay on a much longer scale. In the time to decay, they're already being cooled down because of synchrotron radiation in the magnetic field. Okay, and the interesting thing, obviously, that when mu neutrino and mu antineutrino annihilate into Z naught decay also produces neutrino antineutrino pairs. And interestingly, that some of the tau neutrino, which is not existing in the before, can now be produced by this annihilation process. So it's an interesting thing that in this mechanism, you can produce a very interesting flavor ratio dominated by basically mu neutrino. Then you have this somewhat electron neutrino, and then you also have tau neutrino coming from this annihilation process. The upshot of all this is to try to tell you that if indeed this is the production mechanism by jet for these high energy neutrinos dominated by the muon neutrino kind, and they meet the muon antineutrino converted from beta decay electron antineutrino from this neutron rich material synthesized in this Klapsar accretion disk, then you should expect that above several hundred TeV, the spectrum will be curtailed because the suppression due to the annihilation. And this is much less sensitive to the details of the jet dynamics. You know, you can put it in orders of magnitude variation in the jet energy. You still always have this signature at 260 TeV or so, where the annihilation kicks in efficiently, and the suppression is always going to be of order a factor of 2.5 to 3.5. Okay. The spectra. Yeah. This happens very quickly. So in the sense that simultaneous with the launching of the jet, this essentially happens. The time scale for acceleration is a fraction of a second. Very good, very good. Yeah. Yeah, I will talk about it in the second part. So this one is especially interesting is because of the winged nature of this thing. So you have a wind which is evaporating for a thing. The material which will be able to radiate the neutrinos is being carried out to far distances. And these neutrinos can then annihilate with this high energy neutrino with large angles. Okay, the thing that if you have neutrinos down below and they're radially going out, the flux dies up very quickly, right? So that's the thing. Okay. Alexei, right? I suddenly recognize it's you. So, all right. Okay. All right. All right. So eventually the upshot again is if you assume Klapsar happens quite often, and they are the dominant contributors towards the diffuse flux observed at the ice cube. So these are the data points seen in these all flux observation by the ice cube. And the model we propose essentially can fit all these data pretty well. The more interesting thing here is the following thing. Let's forget about the data points above TeV for now. The ice cube data show that there is a suppression above, say, like several hundred TeV. And this is only an upper limit, which is pretty bad. But nevertheless, it's some kind of constraint. But this is a real data point, except that it has a huge error bars. If you don't have this annihilation thing, you continue the earlier model for producing the high energy neutrinos, and without annihilation, it'll follow this dashed curve. As you can see that basically there's a huge discrepancy in the fluxes at those 2 points, even though this one may be compatible within the error bars, but this one clearly misses it. But if you then put on this annihilation process, you can vary lots of parameters, like how much material is evaporating off the disk material, what's the rate, how many solar mass per second. You can vary a lot. And you can think about the geometry of the wind going off the disk. It doesn't really matter very much. We even talked about the oscillation scenarios where how the electron antineutrinos may oscillate into mu antineutrinos. It doesn't make much difference either. So you always get this suppression naturally. Okay, that's one. Now, what about these guys? Above PeV, that's a solid data point. That we don't think can be explainable by our model for producing high energy neutrinos in this environment. We think that's just a totally different mechanism for producing it. It may not have anything to do with core collapse supernova, right? So that's that. And by the way, I heard that at the most recent neutrino conference in Italy, they announced an event also. It's not just tens of PeV, right? But it's not really official yet, but at least they made an announcement. Yes. Could you? That's right. The inverted order is what we used, but this is basically one of the curve in here is changing the inverted using the normal. It doesn't make any difference. All right. Yeah. So either way, it doesn't make it. The reason is because you already have sufficient probability for these two types of neutrinos to annihilate each other, because the density of the neutrinos is sufficiently high already, and the details of the flux level changed by the oscillation hierarchy doesn't really matter very much. Okay. Okay. Yeah. So very quickly, I'll just talk about what Alexei alluded to. This is very specific. I tailor it to collapsar. I want to tailor it to the ice cube kind of diffuse flux. What about the ordinary things? Let's buy that somehow if you have high energy neutrino, you've got to have a jet. And if you have a jet, you've got to be associated with an accretion disk. And the accretion disk got to be very hot. So first of all, the accretion disk is a neutrino emitter because it's hot, right? It's just like a surface of a neutron star, more or less. And it can dominantly emit electron, neutrino, electron, antineutrino, because as I said, that the electrons in the disk typically are very degenerate. They are basically doing the electron capture on protons, and then it'll turn into electron neutrino. And because it's hot, you have electrons, you have also positrons. Positrons do the other way. So you have positron capture on the neutron and produce proton and electron antineutrino. So dominantly, the accretion disk around black holes typically are dominated by these two flavors. Now, the jet goes out, and at some point, the shock will accelerate these charged particles, and these guys collide with each other, will make neutrino, antineutrinos of the high energy kind. And now you have this simple intersection, all the way from the accretion disk versus the high energy neutrino, and you can then have all sorts of interaction between different flavors. If the neutrino of the two kinds happen to be of the same flavor, then you can annihilate into any kind of fermion anti-fermion pair. But if you're of the different flavor, then obviously you can only turn into, if the meaningful kind of interaction would be turning into each other's charged lepton. Okay, so that's essentially the way you do it. You associated all these processes in this problem, and the characteristic parameters is not much. One is the size of the accretion disk that determines the emission surface. The temperature of the disk tells you how energetic these neutrinos will be of the low energy kind. The other one is the angle of the jet, because that really determines the intersection angle between the low energy neutrino and the high energy neutrino. If these neutrinos are collinear, they don't talk to each other. So the angle for the jet is very important. There are two limits. The simple limits is that the jet is extremely relativistic. So the opening angle is purely determined by the Lorentz factor. The beaming, relativistic beaming is 1 over gamma. The other one is the jet has its own intrinsic geometry. For example, it go from some high density region into a low density region, suddenly it opens up. So this open angle is sort of like another parameter. altogether, the strength of the interaction, the probability of the interaction depends on the energy for the high energy neutrino, the temperature of the accretion disk, the size of the accretion disk, jet opening angle, and where you're going to produce the high energy neutrinos, right? Because how far away from the thing determines how much flux will reach this particular point from the accretion disk. Yep. Yeah, this if bar is all there, the fermion, atom fermion, everything is included. Everything is included in there. Right. Okay. So it turns out that the results in the end is very simple. The overall effect of this kind of interaction, low energy neutrino, high energy neutrino interaction, is characterized by the survivable probability for the high energy neutrino. There's a characteristic energy at which this effect sets in, and the modification of the original spectrum is basically just like a semi-power law thing. Okay, you can see that if energy is too low, it doesn't change anything. When energy is around E0 or more, then it suppresses by this extra power index N. And this threshold energy is exactly inversely proportional to the strength of the interaction. That is, the more likely you're going to interact, then the lower the energy threshold, right? And so in a sense that you can see that it has all these slopes in this logarithmic diagram, the power law essentially go like straight lines. And the power law index over here follows, again, some kind of scaling law with this strength of the interaction. I mean, it looks a bit more complicated, but nevertheless, the power law index for one case, let's say if you assume the intersection angle mostly is constrained by the Lorentz factor of the jet, the index go from 0.4 to 0.6, so around 0.5-ish or so. And if you think about the suppression, I mean, the opening angle is more intrinsically to the jet itself, then the index of suppression could be even larger, okay? And so ultimately, what you see here is not only the suppression of the flux in this additional power law on the tail, and the other one is the flavor ratio, because obviously the energy of the high energy neutrino determines how much likely it will interact with the low energy neutrino. So the flavor ratio for the muon to electron kind of the high energy neutrino, typically we talk about the 2 to 1 at the source, but because of the annihilation process, now it depends on the energy. And also, it also depends on the oscillation scenario, because now from the disk to the annihilation point, there's a lot of distance to go through. There are many, many possibilities for the flavor oscillation to happen. And this is a weird kind of thing is that you'll see that the flavor ratio for mu to E would increase with energy. And for example, in other scenarios, it has these ratio, which is fall below 2, which is all kind of a characteristic of this particular process. Exotic really means that the electron, neutrino, and antineutrino both convert to the mu flavor. So this is like a sort of exotic collective oscillation, but it's not really a detailed calculation. It's just map out the limits. Okay, so I sort of like finish here. I give you 2 interesting scenarios where in this multi-messenger era, actually we could resort to high energy neutrino observations, try to understand these sources which are producing very interesting heavy nuclei through the rapid neutron capture process. And even though the neutron-rich nuclear synthesis mostly is in the low energy domain, but somehow it has this manifestation in the high energy phenomena. Thank you.
Okay, time for questions and comments further. Okay.
So thanks for the nice talk. I was just wondering for the diffuse flux plot, exactly this plot.
Yep.
These are jets associated, so you would also presume a beaming prediction, right?
No, it's essentially all kind of normalized already. So you say that basically what we say that, look, the biggest uncertainty is that how often collapse will occur and do this, right? And so all you need to do is to say that, first of all, we know the supernova rate, and we have an upper limit for that, how many of them can go under core collapse to give you this collapse phenomena. And it's a sizable fraction, like a few percent, okay? So a few percent of the supernova rate, and if you then normalize to the whatever the amount of high energy, cosmic rays produced from this thing, again, within the limit, you can easily explain the data points. So that's essentially the flux normalization. And correct. And it already take into account all the beaming, all that. Right, yeah. It actually doesn't matter in our case, because you see that the problem, not problem, the geometry we have in this problem is very much dominated by the distribution of the low energy neutrinos, because you have a wind goes out, and you are essentially launching the jet in this semi-isotropic neutrino gas of the low energy kind. And then these low energy kind, because the beta decay obviously is almost isotropic in emitting the neutrinos, so it can go in any direction you want. So this 1 minus cosine theta thing is dominantly contributed, determined by this geometry of the low energy neutrino kind. So even if you have an opening angle, it won't enhance this thing very much. If you have a very narrow thing, it doesn't shrink it either. It's very different from the case where I later on talk about the accretion disk. The accretion disk, then you have to worry about where you're going to meet the darn thing, right? So if this thing is very far away from here, the accretion disk looks like a point. And then both go collinear, then it really depends on how the jet opening angle going to go. But this thing is very different, because you are immersed in this low energy gas of all the neutrinos, and it basically is isotropically distributed in this low energy gas.
So I would like to know, in the first part of your talk, when you discussed about the flux of the neutrinos, so would there be any situations where say for the muon, when it decays to, as you're saying, electron and the muon neutrinos, so could there be any situation where the decay can be blocked, because it always depends on the Fermi energies, right?
Yeah.
So if I consider the electron Fermi energy is all field, so the muon decay can be blocked, right? So in that case, the fractions of the the flux of the muon will.
This is very, very different environment from the dense environment of the neutron star, where you worry about polyblocking all the time. So even though in this kind of environment, I don't remember the density now. It's so low that the electron neutrino, you essentially really talk about the real particle physics. You don't worry about the environment, the medium effects very much. It's so far out. The only medium effects, quote unquote, medium effects you worry about is magnetic fields, because all the charged particles in the magnetic fields lose energy by synchrotron radiation. And these other particle processes I highlighted over here, for example, not only synchrotron radiation in the magnetic field, you also scatter on the photons in the environment. So photons are more like the medium here. And when they scatter on the photons, you can create electron-positron pairs. These are the dominant processes which kills off the high energy charged particles. And that is taken into account in this model. Yeah.
Second part of that, if you discuss about the new pair energies to the effect bar. So in the formula, do you also consider about because it's coming from part sources, so is there any redshift vectors that should be taken into account, or?
This is entirely in the source itself. We only talk about within the source how the original high energy neutrino spectrum of flavor ratio will be modified. Once it goes out of the source, you have to take into account all the redshift effects and such. But in this diagram, where we talk about diffuse flux at the ice cube, we did take into account the redshift effect, because we are summing all the possible cosmic sources And typical redshift where the star formation rate peaks is about 1. So essentially, that there is a redshift effect of 1 plus z in this plot. Right.
Okay.
You have multiple different sources that can contribute to the different pricing. How many of those sources can reset this annihilate within the tree? Can we expect all of them or?
Okay, so I'm a very simple-minded person. I like to under one thing at a time. So my motivation over here, obviously, is very much driven by the sources for the process nuclei. So I focus only on this particular source. And you're right, this is essentially an upper limit in the sense that it could have this contribution towards the ice-cube diffuse flux. But if you want to say that allow for other kind of sources, it will basically modify some of the contribution towards it. But no matter what, I think that these kind of a sharp drop in the spectral thing is something to be explained. In this kind of model, it happened to be explainable by this annihilation effect. In other kind of model, if they're also substantially contributing towards this diffuse flux, you have to resort to other kind of things. And because they may not have this low energy neutrino source to do the job anymore. Right. Okay.
We know that very often the environment is very hard to calculate in the short and which, I mean, these are really high energy. You mentioned like heating or.
Yep. Yep. Yeah, that's a very crucial question. That's why I call it a simple model without it being said this is self-consistently being done. If somebody actually simulated the collapsar formation of an accretion disk and a jet and everything is self-consistently done, that's no longer a model. That's really kind of almost a truth, right? But the thing here that what we rely on the two things. You're right that this kind of environment are typically going to be radiation dominated, and under radiation dominated conditions, it's very hard to accelerate the charged particles. But there are also interesting things in the sense that if somehow, again, this is mostly coming from this kind of theoretical arguments plus some set of these simulations. But if you have the jet magnetized mildly, there's some energy density in magnetic field compared with the thermal energy content is about roughly 10% or so. In those situations, you can have these subshocks. The subshock themselves are not extremely radiation dominated. They are basically collisionless. Even though the efficiency for accelerating goes down compared with the regular collisionless shock, but because of the existence of subshocks, you still can do the acceleration. So in the sense that it can still do it, whether they can really accelerate it to the energy required for this mechanism, people are still arguing about it. But to us, this is a possible way this can be done. That's essentially how this thing is done. Basically, you can see that the typical acceleration models would give you mu and mu antineutrinos comparable. We have a huge suppression of the mu antineutrino simply because pion can decay fine, but once the product's muon want to decay, you waited too long, it's already being cooled down by the synchrotron radiation. So all this thing is taken into account.
I have a general question on the R process nucleosynthesis calculations.
Sure.
Is there have been studies of the uncertainties on the abundances implementing our misknowledge of exotic nuclei properties like masses, half-lives, neutron capture rates, because as you know, that involves thousands of nuclei. And many of these nuclei are not well known. They cannot be measured in experiments like fission products. So have there been studies of the impact of these uncertainties?
Yeah, that's essentially an industry, right? I mean, you'll hear more talks by speakers later in the week and the week following. I think Rebecca Sermon and Gail McLaughlin, they are the ones who will answer your question more professionally. But I can tell you that all this thing is doesn't rely on the details. We do know that if you go on very neutral side, you definitely beta decay towards that. And the typical beta decay energy is, less than 10 MeV, and that's and above maybe several MeV. Typically, that's we know, right? So all that is essentially in the growth part of the thing, which is used in this model. But you're right. If I wanted to eventually to tell me what exactly is the distribution of the nucleus coming from this process, then it all depends on those details about nuclear systematics. And then that will be the crucial thing. And I think, we're not only just theory, you really rely on some experimental guidance to help us, right?
Sure. Yeah, the cross feature, yes, but what's going to be the uncertainty? But I will ask the question to Rebecca then.
Okay,
Thank you very much. Thank you for this very interesting talk.